Alright, so with our first lecture, we start with a continuation of what we ended in discrete math 1, and that was about induction. So 5.1, that was induction. And perhaps it's good that I repeat what that was. Induction was a way of proving things in a bit strange way. Namely, there are two things you have to do in induction. So you're trying to prove a certain property of a number n. It's about induction always is about natural numbers. Discrete math, if you know, is for us quite often about natural numbers, although we'll see that that's not the only objects that we will study. But anyway, so Pn is a property about the natural numbers. So for instance, n is even, n is a prime number, God knows what, or a more complicated proposition about the natural number n. And to prove that Pn is true for all n, so is Pn true? That's the question. There are two steps. So induction says there are two things you have to do. First of all, you have to show that you can start. So P0 is true. P0 being the first number. Now, it depends a little bit on the situation what actually is the first number. So we have to be a bit flexible. Sometimes we are proving something about natural numbers that are positive, and 0 is not considered positive. So, and then the first number would be 1, right? Okay, so P0 is true. That we call that the initial step. And as I said, initial can be a little bit depending on the problem. Often it's 0, but it could be 1, or it could be even higher. Okay. And the second thing that you have to prove, and that's the weird thing, is assume that Pn is true. So you're not proving Pn, you're assuming it true, but what you have to do is prove now that Pn plus 1 is true. This is weird, right? It seems like you're putting yourself up on your own shoestrings. So you assume the truth of a statement to prove not the same statement, of course, because that would be not a valid proof. Then everything would be true, right? If you can just assume that something is true and then follow, and from that it follows, of course, that it is true. But the thing is, you assuming some statement, Pn, but you're going one further. Okay. Now the picture one often makes is that this is kind of the same as being able to go up on a ladder. If you know that once you're on somewhere on the ladder, you know how to go up the next step of the ladder. If you know how to do that, like you say a baby, and the baby's figured out how to go from one stair to the next stair. Let's talk about stairs. Babies don't climb ladders so easily. Okay, so the baby knows how to go from one stair to the next stair. Then it follows that he's going to be able to go up on any stair, well, reasonably high, of course, he's going to get out of breath. But in principle, he can go on any stair, because if he has a stair, let's say, there's a staircase of five steps, well, he knows how to go on the first step. And once he's on the first step, he knows how to go to the second step. And from the second step, he knows to go to the third step. So each time when he is on the third step, we apply this principle here. This is, I am on the third step, and now I know how to go on the fourth step. Okay, that's what this means. That's the principle of induction. And I'm going to give you one example of how we can use this. It was a homework problem from last time, from discrete math 1, but I don't think it was assigned, so I'll do this. So the Pn is the following statement. So the first thing, of course, is identifying the statement. Sometimes things are put in words, that makes it harder, but here it's a formula. So the formula says that if you take 1 times 1 factorial plus 2 times 2 factorial plus ... plus n times n factorial, then that is equal to n plus 1 factorial minus 1. That's now, first of all, the ... is a little bit weird here, right? So let's think about what is this ... That means that there's a pattern here that is obviously clear. We go from 1 to 2 to 3 to 4 and so on until we reach n. And n is being the index, if you want, of the statement. Okay? And so we have a left-hand side and we have a right-hand side. The right-hand side is much more compact. And it says that the left-hand side is the same as the right-hand side for no matter what n is. So this is the theorem. And so now we want to prove this. So the proof... Well, as I said, there are two things. Yeah, sorry, this I should give the name to this. This is the induction step. And the word step, really, you have this image that you have from the ladder, climbing up a ladder, right? Okay. So the proof, let's start with the initial step. While I'm explaining this, I should point out that one of the hardest things is sometimes to know how to write this down. So always make very clear what is your initial step, what is your induction step, and be very systematic in that. Okay, so follow the way I do this. Initial step. Well, there's no, well, from the form here it seems we have to start with 1. So let's add this for all n bigger than 1, we have this statement here. Okay, that's what we're going to prove. So that's, if you want, a theorem. A theorem in the natural about numbers. So the initial step is, here the initial step therefore is n equals 1. So P1. We put a question mark, we don't know yet that P1 is true. This is different, right? In the initial step, you have to prove that that initial step is true. Okay, what is P1? P1 is the formula. Now, how do you do this? So, what is P1 say? P1 has two sides, right? It's an equation, and one side it's 1 times 1 factorial, and we go all the way to n factorial, but n is 1, so it ends there. Okay? Now, equals 2, right? This is the equals 2, but we are questioning this, so I'm going to write this as, let me put it with the red here, is this really true? And now I copy what the formula here says. 1, so n is 1, so plugging 1 in here, so this is an n, which is now 1 plus 1, that is 2 factorial minus 1. Is this true? Well, let's work out everything here. 1 times 1 factorial. 1 factorial is 1, right? So this whole thing is 1. And on this side, what we get, 2 factorial is 1 times 2, that's 2, minus 1, that is 1. Yeah, that is okay. These things are the same. So our initial step is done. That's often the easier one. And so, but it is important, it cannot be skipped. And it's the easier one, it's a hint, oh, this is where you can get extra, at least some points. If you completely lost, at least to the initial step. Okay, now the induction step. And that is a little bit, as I said, the organization is sometimes a little bit difficult here. But okay, let's do this. So induction steps, we assume Pn. In other words, Pn, let's write out again what Pn says, is 1 times 1 factorial plus 2 times 2 factorial plus ... plus n times n factorial equals n plus 1 factorial minus 1. Now assume, that means this is something that we can take for granted. So let me put this with a check on mark here. We know that this is equal. Now, but there's two parts, right? So assume this one. Now we have to then, we should perhaps add that, right? You start with assumption and then you prove this. So to prove, let's write it this way, to prove Pn plus 1. Well, let's also write down what Pn plus 1 says. But remember, now it's something that we need to prove. So instead of a check mark, we're going to have to put a question mark on top, the equal sign. Okay, 1 times 1 factorial plus 2 times 2 factorial plus all the way. How far do we go now? We go to n plus 1. Okay, so we go all the way up to n plus 1 times n plus 1 factorial. Why this? Why this expression? And this is important. Why this? Well, what is the difference between Pn and Pn plus 1? Well, instead of n, we have n plus 1. So wherever we have an n in here, we have to replace this n by n plus 1 in here. So this n has to become n plus 1, but there's more than one n. There's this n has to be n plus 1. And that's only the left-hand side. What about the right-hand side? Equals, but I'll already put it here, we don't know, so I'm going to put a big question mark over it. What is on the right? What do we get on the other side? On this side, well, again, we have to replace n by n plus 1. Okay, keep that in mind. It's replacing n plus 1. So we get n plus 1 plus 1. What do we get? N plus 2, right? So we get n plus 2 factorial minus 1. So that's what we need to prove, and that's what we have. So this is what we need to prove, and this is what we have. Okay, now, how do we do this? When you have an expression, it's always often you work with the more complicated one. This is the more complicated one because of the dots in there. And you try to link this to what you know. Now, I left a little bit space. Why do I do that? Because I want to think about what is the term that comes here just before my last term. it would be 1 less, right? Remember, we go always up by 1. In other words, if you think this way, we go down by 1. Okay, so what is this term here? So let me write down. This term would be n times n factorial, right? I don't have to write that. Right? That's the term just before it. And then you could ask what's the term just before that, but let's not answer that. Why do I say this? Why do I make this explicit? Because look now, we have a match here. This part matches this part. Okay? So these two blue things are the same. But here we have a check mark, so this blue thing is also equal to this blue thing. So we can replace this whole blue thing by n plus 1 factorial minus 1. We have a check mark. It means we have equality. We can do that. Okay, but we have still one more term left, this one. So let's write that also. Plus n plus 1, n plus 1 factorial. Okay, I'm going to work on this left-hand side. I'm going to leave the right-hand side. Often we leave the right-hand side or the less complicated side. Okay, often that's the right-hand side. And we work with the left-hand side until we get to the right-hand side. It's not always possible, but that's what you try to do. What can we do now? So I have this expression. So this is what I'm dealing with here, right? So this is somehow I have to get it in a simpler form. It's clear this is simpler, so let's try to simplify this. Can I simplify this? It's what we have here. We have this n plus 1 factorial and an n plus 1 factorial, so we can combine them, but we have to be careful, algebra, right? So this is a quantity, this is the quantity, and this is the quantity, and this is the quantity. So how can we combine them? So it is, I'm going to switch the minus 1, that's what this one, n plus 1 factorial, plus n plus 1, n plus 1 factorial, minus 1. Okay, I just switched the order. Now let's factor out an n plus 1 factorial. Sorry, let's factor out this term, n plus 1 factorial in these two. N plus 1 factorial. So what is left if I do this? If I factor this out in the first term, there's only a 1 left, right? So there's a 1. What happens if I factor it out in the second term? There's this part, n plus 1 left. And of course, in between is an n. Okay. So, minus 1. That is equal, right? The minus 1 is still there. I cannot do anything with that. What is this? We have n plus 1 factorial times n plus 2 minus 1. Am I where I've got? I have an n plus 2, but it's not the right shape. It's starts looking this n plus 2, but there's a factorial here, and the factorial is there. Oh my god, what is going on? Well, now it's just a thing you have to just think a little bit out. What are these things? N plus 1 factorial, what is that? Remember, the factorial is all the numbers multiplied until the very end. Okay, so n plus 1 factorial is, this is, what is this? Let's write this down. N factorial is 1 times 2 times 3, again the dot dot dot, all the way up to n plus 1. Okay. Now if I multiply this now further with n plus 2, so this is actually what this whole thing here now is, what do we get? Well, that is just n plus 2 factorial. That is just the definition of n plus 2 factorial. So what I actually get here is n plus 2 factorial minus 1. Hey, but that's exactly what I wanted. Now, this part is equal to this part. And so I proved this. Okay? Remember, I went from the left-hand side and worked all my way to get the right-hand side. That's considered a proof. And where was the induction step? It is by looking at this part here. Okay, now that's induction. That's not what this is about, our topic today. Our topic today is about strong induction. So what's the difference? The difference is in here, in this part, in the induction step. In strong induction, so what do you do in induction? Induction, you go from one to the next. In strong induction, you go slightly different. You go from the previous to the next. Now, previous in plural, meaning all the possible previous cases that you have, you go and you prove the next one. So I'm going to write it down, but writing this down is less instructive than actually working it out. So, but I have to write it down. So strong induction is the following thing. Approved by strong induction, you do two things. The same thing, P0, the initial step, That's still true. So prove the initial step. So this is a proof by strong induction. How does it work? What's the scheme? First of all, you prove P0, the first initial step. That hasn't changed, as I told you. Now here is so assume P and Pk is true for all k less than or equal to n. That's what I mean with all the previous cases. So not only Pn is true, but Pn minus 1, Pn minus 2, P all the way down until P0. Okay? So assume that all these things are true. That's a lot that you can assume, right? And then to prove, and that is again the same. Prove now that the next one. These are everything up to n. Well, now the next one is n plus 1. Okay? So let's perhaps look at first, why is this? I'm not going to tell you that this is a valid principle. In fact, the book gives an explanation for that. So you remember, I'm going to assign you reading assignments. Not everything that I do in these videos will be, not everything in the book will be explained in the videos, but in the videos I always work on, will give the most important things. But you should read also the book. And in the book they show you how the strong induction principle actually follows from the induction principle. And it's called strong induction because it's stronger, right? Because why is it stronger? Because you are allowed to assume more. You have more things to work with instead of, because for all k less than n, in particular for n itself, so Pn itself is true. So this part here, this induction step in regular induction is only part of your assumptions. Okay, so that's why it's stronger. Okay, so but let's look at this ladder. Now suppose you design, let's not work with babies anymore, let's work with a robot. And you have a robot that knows how to go on, so whenever it sees a ladder, it knows how to go on the first step of a ladder or on the second step of the ladder. So you program it to do that. So whenever it finds a ladder, it says, okay, it looks for the first step and it looks for the second step, and it knows how to get on either one of those. Okay? So let's write it down. So P is the statement can get on, so Pn is the statement can get on the nth step of a ladder. Okay, this is robot can do this. You have designed it to do that. Okay, so that's the first thing. So it can do P1, it can do the first step, and it can also do the second step. Okay. Furthermore, it knows once it's on a step, it knows how to go up 2 steps. Yeah. Let's say its mechanism needs there to be an extra step. So it puts one leg on the first step and then climbs all the way up to the second step. Can you imagine some kind of crawling robot? So if he is on space n, he knows how to go 2 higher. Okay? I'm not saying that he knows how to go 1 higher. And probably because in his way he has to crawl, he cannot do that. He needs more space. Okay? So now you're going to say, oh, but hey, that's not going to work now. He cannot go on every step now. There's a problem here, right? Because he only goes by 2s. So how is he going to, he's skipping steps. My claim is he doesn't. Okay? So my claim is still, if a robot can do this, then it can go on, then it can get on any step, then, in other words, Pn holds for all n. Let me write it this way. Then Pn is true always. Now, if I try to prove this with induction, I cannot do that, right? Because induction, okay, let's try to prove this with induction. It's a good test. So there are 2 things we have to do. The initial step, P0, well, we started from 1, so P1. So is P1 true? Well, yeah, because we told it is true. Okay, so sorry, when I wrote this here, I mean these are true, right? Or possible, whatever you want to say. Okay, so that the initial step is clearly okay, because I just told you it's okay. Now, what about this step? If you're on a step, can you go 1 step higher? No, you cannot. That's the problem. If you're on a step, you can go 2 steps higher. So we cannot apply induction here, it seems. The proof by induction does not work. But the proof by strong induction works. That's the cute thing. Okay, let's try to do this. Okay, so the proof by strong induction. I'll be a bit careful, there's a lot of, so proof by strong induction. I have to show that Pn is always true. Okay, I have to show the initial step. So the initial step, let me write it up. P1. Is P1 true? Yes, because I'm telling you. Not only did I tell you that P1 is true, I even told you that P2 is also true. Perhaps I was just being generous in my information, but okay. And anyways, so this tells me, green. Okay, so this is okay. Initial step is okay. Now, what is the induction step? Suppose Pk is true for all q at less than or equal to n, right? This is exactly what the assumption is. To prove the next one. To prove Pn plus 1. You say, oh, but professor, no, we know that if Pn is true, he knows it, you don't know how to go up one step, he knows how to go 2 steps. Yeah, but, okay, he's on this particular step, right? And he has to go up 1 more step, and he doesn't know how to do that. But we said not only does he know how to go on the step that we are currently standing, he also knows how to go on the step just below that. He knows to go to all the steps below or equal to that particular step. That's what this says. So let's start over with this robot and let him not get on the step where we're standing, but let him getting on a step lower. Now that he's on that step lower, so the proof goes as this, right? Pn minus 1 is true. Why? Because it's 1 lower, right? We know that he can go up all the steps up to and including the end step. That he can go all the way up and to the end floor, let's call it that, okay? In particular, he knows how to go up to 1 floor less, 1 step less. So Pn minus 1 is true. Now, by virtue of his design, he knows how to go 2 higher. So Pn minus 1 plus 2 is true, right? He knows how to go 2 higher, but what is that? That's just Pn plus 1. Now he is on that 1 step higher. Now we have to be a little bit careful, okay? When I say this, assume Pk true for all k, this is for all k, that all natural numbers starting from the initial number. Of course, here we started not from 0, here we started from 1, right? We started from step 1. You could have labeled the steps by 0th step, 1st step, 2nd step. That's fine, right? That's when stories like that, for instance, in Europe, that's how they count stories. The ground floor is considered the 0th floor, and then what we call the 2nd floor in Europe, they call the 1st floor. But that's just a counting thing. So, but here we started with 1, so we have to do this for all k between 1 and n. Okay, because we don't know about anything else. Now there is a little thing that we have to be careful about, n minus 1. Okay, so I'm proving the case Pn. Okay, am I sure that n minus 1 is actually not too small here? So what if n is 1, then n minus 1 would be 0, right? And we don't know anything about 0. But if we're dealing with P1, that's if n is 1, then we're trying to figure out, can we get to 1 higher? And in this case, that would be P2. So if n is 1, so we have to make a little thing here. If n is 1, if we are on the 1st step, can we go to the 2nd step? Then P2 is true. Why? Because we are told that it is true. So this was not spurious information. We needed that. Okay? If n is 1, then P2 holds. Because it has nothing to do with n. We know that P2 is true. So if n is bigger than 1, well, then n minus 1 is bigger than or equal to 1, and then we are in the right range. It's a slight detail, but it's sometimes important. But don't worry too much about that. Okay, so that's the principle of strong induction, and I hope that I not only convince you that it works, but it also that it is useful in this kind of thing. So let's do, I'll do two problems. First one is a nice one, actually. It's an actual serious theorem. The theorem of arithmetic says that any number n bigger than 1 can be written as a product of primes. We used this, of course, already in discrete 1. That is the case. This is, let's say, general knowledge, so to speak. But we're going to prove this now. Okay, so how does this work? So what is Pn here? So proof. Okay, proof. The first thing is, as I said, it doesn't always come this nicely on a platter. So what is Pn here? Pn is the statement that n is a product of primes. Okay, so what's the initial step? So we're going to do a proof by strong induction. Let me add this here. Yeah, if you do, and at some point you're going to do proofs, you have to always tell me what method of proof you use. So proof by strong induction. Okay, initial step. What is the initial step here? Well, I said n has to be bigger than 1. So the first number this applies is 2, P2. Is 2 a product of primes? Yes, because 2 is a prime. That's considered a product of primes, right? If you just on your own, that's already a product. I hope you agree with that. Okay. So then that's the initial step, and then let's now prove the general step. Okay, so what is that? The induction hypothesis. Assume that pk, is true for all k. Let's say, from where does k go? Well, we start from 2, 3, etc., all the way up to n. Okay? This is so you see that in regular induction, there's only the n that we talk about. In strong induction, there is also this k, right? That is kind of keeps track. It's don't pay too much attention to this k. It just means all previous cases, all cases from Pn and before that. That's what it means. Okay, it sometimes throws people off this extra variable k there. It's not really, it doesn't play a role. We're not using it in the way that we use n and work with n. Okay, pk for all k up to n. So to show Pn plus 1, the next one. Okay. Now what is also typical sometimes of these proofs is that you cannot just always do the same strategy. And so we have to consider two cases. Case 1, n plus 1 is a prime number. Okay. And so what we have to show about this number, that is a product of primes. Duh, it's a prime number, that's a product of primes, that's automatic. So let's call this, okay, let me put a little bit here. So this is now what we're trying to figure out. Now, what this says is that if n plus 1 is prime, then Pn plus 1 is definitely true. Okay, that's great. So in this case, it's already done. So proof by cases, remember, you have to make sure that you cover all possibilities and then prove for each possibility that it's true. Now, what's the other possibility? That n plus 1 is not prime. Another way of saying that is it is composite. Okay, what does this mean? Means that n plus 1 can be written as a times b, where a and b are numbers at least 2. Okay, that means to composite, right? To be not a prime means that you can written as a product of two numbers that are not 1. Okay, that's that. Now, in particular, a and b, how big can they be? Well, they must be smaller than n plus 1, right? They're smaller than n plus 1, so a and b are less than n, or equal to. They could be equal, and it's not really possible, but it could be, okay? In other words, they fall within the range of these assumptions here. These are special values for k. A and b are both satisfy are within this range. So that's why I say this k is really just a way for us to write down the range of which this proposition is true. And so here these are two elements that fall in this range. So we know, so by induction hypothesis, often written IH, right, induction hypothesis. By the induction hypothesis, we know that PA is true and PB is true. Now what does this mean? PA means that A is a product of primes, and BB means that B is a product of primes. Okay? Now, you see that we are almost there? Because what are we talking about? We need to say something about n plus 1, which is the product of these two guys, and each of those are product of primes. It's no big leap of faith. I mean, it's just clear, right, that if this is a product of primes, this is a product of primes, then A times B is a product of primes, and this is exactly what we needed. So we're done. So you see, a lot of what I said I said it in words, I didn't even write it down. Now, when you write it down, you have to give a little bit more, you have to write this down, right? When you make a proof like that, you have to write it down. Okay, so I do one more example, because most of these problems, and homework problems, will be on this tip, of this nature. So, Pn is the statement if for all n at least 12. So you see that sometimes it doesn't have to be start from 0, 1. It can start from, for all n at least 12, n postage of n cents can be made using only 4-cent stamps and or 5-cent stamps. Okay, so in other words, what happens? You went to the post office and said, sorry, we are out of this particular, one cent stamps and so on. The only thing we have are a booklet of 4 cents and a booklet of 5 cents. And you say, okay, give me enough. Give me like 20 of each, because I want to make more postage that I want to make. Of course, you need a lot of them. If you want to make 1,000,000 cents, if you're going to make postage of 1,000,000 cents, you're going to have to buy a lot of those. Okay, but the assumption is you have unlimited resources of 4-cent stamps and 5-cent stamps, and then you have to show that you can make any postage. Well, not any, obviously. How are you going to make 3, right? How are you going to make 3 cents? You cannot do that, because the least you can do is 4 cents. So what about 6 cents? It doesn't work either, right? Because 6 cents, how are you going to do 6 cents? Notice that you can do 9 cents. But I'm not even claiming that you can do 9 cents. I'm claiming everything that is at least 12 I can do. Which is a silly question, of course. It never happens, but it is cute. No? Okay, so proof by strong induction. Okay, so what's the initial step? What is the initial step? Remember, in this kind of, when I ask questions, it kind of is a hint to you, oh, I should stop, I should pause and think about it, and then see where I can answer this. So perhaps try already this, just pause the video and try to solve this problem, and see how far you get. And then perhaps there's a step you missed, and then once you realize this, oh, cool, now I know what to do. So every time pause this video, be very active here. Don't just passively watch this video and then fall asleep halfway, okay? Initial step. What is the initial step? P12, right? We start with 12. Now, is P12 true? That's the question, right? So remember, we have to prove this. P12 true. So can I make 12 cents using 4s and 5s? Yes, that's 4 plus 4 plus 4. 3 of those stamps will take care of it. And that's the proof. Okay, so that's done. As I said, the initial step is always often easy. So now the induction step. So what does it mean? Assume PK is true for all k at most n. Again, writing this down formally is harder than saying it in words. What is it that I'm assuming? I'm assuming anything up to n I can do. at least, well, starting from 12. Okay, anything, so right, so perhaps I should make this 12, put that there. Okay, so now I have to do n plus 1. So to prove, sorry, to prove, so there's always two parts, right? You assume something and then to prove Pn plus 1. Okay, so what I want to do is the following. I want to look at, I'm going to use one of my stems. Think about the robot, right? The robot was on a step and he had to go one step up, but he couldn't do that. He can only go by 2 steps. So we had to tell the robot, come down, and go not up to the step that you were standing, but go one lower, because you know to do that too. So he goes there, and now he goes up by 2. Okay? So what we're dealing here is basically the same. A robot that can go either 4 or 5 up. So we want to go to n minus 3. That is 4 less than n plus 1. Because if I know how to do n minus 3, then how do I do n plus 1? Well, you add another 4 cents and you're done. Okay, so Pn minus 3. But there is always a bit of a problem. When I subtract 3 from it, I have to make sure that I stay above 12. So in our induction step, although we only need to do P12, we need to know a little bit more. Because when are we going to be in problem? Well, we are in problem when n is 13 or 14. So what about n equals 13, n equals 14, and n equals 15? Okay. Now, n equals 15, I guess, is okay, because I know how to do that, right? Let me think. If n is 15... Yeah, I think that is okay. All right, so these two. So because I want to make sure that this n minus 3 has to be... So what am I assuming, therefore? I'm assuming that n is at least 15. If n is at least 15, then if I subtract 3 from it, then I'm within the admissible range. And so in other words, I'm going to skip a little bit. I've omitted something that I needed to do. But let me go on to my argument in general. If n is at least 15, I subtract 3 from it, then I'm fine, right? Because then I'm at least 12. And I know by my induction step, my induction hypothesis, this is what we call the induction hypothesis here, right? This part here. We know that I can do it. This is less than my n or equal to, so I know how to do this. So can be done. So whatever postage that is, now add a 4-cent stamp and you're done. Right? Because n minus 3 is the number of stamps, and now you add a 4 stamp, that gives you n plus 1. So n minus 3 plus 4 is n plus 1. Okay? Here, you can do this by a certain amount of stamps, and we don't know yet how, we don't exactly know how, but we know we can do it. Right? There are going to be a number of 4 stamps, a number of 5 stamps, but somehow they make up n minus 3, and now I add another 4 stamp to it, and I'm done. I'm n plus 1. But I could only work this from n equals 15. So my induction step, although I only in principle needed to do P12, I should also check that it is true for P13 and P14. So so in other words, we have to add here. Okay, so we add, let me do this here. Add the cases P13, P14. Now P13, can we do this? Let's think about it. 13 can be written as 4 plus 4 plus 5. So yes, right? That's what it means, right? To make 13-cent postage is this way. Can we do 14? 4 plus 5 plus 5. So yes. And that's it. So now let's go over the proof one more time. We have to show that we can make this for all values n. at least 12. For 12, I know how to do this. But I realize I should also show you how to do it for 13 and for 14, very explicitly. Okay? If you want, this coincides with what here happened here with our, sorry, not coincide, it's similar to what happened to our robot. A robot needed to know how to go up the first step and how to go up the second step. It was necessary that he knows both, right? If you think about it, how does he get on the 7th step? If he goes on the first step, then he goes on the 3rd, on the 5th and the 7th, no problem. How does he go to the 8th step? Well, then he has the first step on the 2nd, then the 3rd, then the 6th, and then the 8th. So it depends on where he wants to go that he has to start from, and the same is true here. Okay, so not only did we need to know 12, but you also need to know what happens with 13, because we know, but it's clear how to do that. 14 is clear how to do that. I mean, 15 is also clear. If I wanted to do that, to be sure, I could write that. Now, it's enough, because once I am at 15, what I'm going to look at is minus 3. The number n minus 3, and if I do n minus 3, then that is at least 12, and I know how to do it for 12. I just showed you. Okay, and this is the part of the claim. Sorry, I should say it this way. I misspoke a little bit. If n is at least 15, then n minus 3 is at least 12, and therefore is within the range of where I know it can be done. So I know this can be done. Do it, add 4, and you're done with n plus 1. That's how proof by strong induction works. Okay. Oh, sorry, that's not what I wanted to do. It's getting a long video, but I do a very, very quick one. A game here, the game of matches. And I'm not going to do it formally. I'm going to just show you. So let's imagine you make 2 piles, okay, of matches. So these are supposed to be matches. Sorry, I'm not very good in drawing this. So, and both piles have the same number of matches. In this case, 2, 4, 6, 8, 10, 12, 14. So there are n matches in both piles, so n and n. Now here's the game. There are 2 players, yeah, player 1, player A, player Alice, and player Bob. Let's go use the same name that we used for cryptography, right? So player Alice has to take from one of these piles as many matches as you want, okay? And Bob the same. Now, the player wins if he takes the last match. If he empties, if the whole thing, if he's the one that makes it empty, okay? So, can Alice win? Not right away, right? Because even if she takes all of one side, should she do that? Should she take everything from one side? No, because then Bob knows what to do. He's going to take everything from the other side and he won. So that's not good, Alice. So perhaps she should take a little bit less, perhaps all but one. Okay, so now the question, the claim is, for Pn is Bob wins the n match game. Or can win. Can win. Of course, he can be stupid, right? If he's a baby, he doesn't know and he messes the whole thing up. But if he knows how to play well, then Bob can win the n match game. That's the statement that I want to prove. Okay? So, by strong induction. And I'm not going to work it out in details. So, I leave the details to you that's written out in the textbook. But here it's how and what it reveals is not just that it can be done, it, in fact, the proof gives the strategy, right? I'm saying he can win. If he just randomly takes something, she takes something from the first pile and he takes a little bit more of that pile, it might not work, okay? In fact, that would be wrong, as we will see. So here's what happens. So let's make Alice, let's make Alice red because she's going to lose. So this is Alice, and then this is Bob in green. So let's start Alice. Alice does something. We don't know which part and we don't know how much. I'm just going to make a choice. Suppose she takes this away. So this goes away. Now what should Bob do? Okay? We are trying to show that in this case, remember what induction proof is. That this is now a new game. It's a game with one more match than then he knows how to win all the matches up to now, but now we have put one more match in it, okay? And now is the question, can you win this game? So what happens? She takes away some matches, but by doing that, the number of matches in one pile is now less than the given amount. Now, what does Bob do? Bob says, I know how to win if both piles have the same size, right? Because that's exactly the assumption. Everything up to now, with one match in each pile less, right? So everything up to there, all possible stacks that are below this green line, if they're the same size, I know how to win. So what should I do? Make a stack of the same size, right? So I'm gonna just take the same number she did. Where is this? Where is my green? Was it 2, 4, 6? 2, no, what did she take here? 5, right? Sorry. I'm gonna do the same thing and take this away. Now look what we have. Sorry, my lines were not really aligned. Here, we have now 2 stacks again. This is 2, 2, 4, 6, 8, 2, 4, 6, 8. No, sorry, I made a mistake. I'm sorry, by drawing, I guess I lost, sorry. I think what happened is I accidentally erased something. Let me make, look, it looks very clear that this stack is not the same, right? I think I accidentally erased something here, yeah? Okay, so, right. So she takes this bunch of 2, 4, 1, 2, 3, 4, 5 of them, he takes away, and Bob says, okay, I'm doing exactly what you do, but in the other pile. I'm just going to also take these 5 away. And now we are in a game that I know how to win, because this game has less than the number of matches that we started with now, and I know how to win such a game. So now that's the strategy as well as the proof. That's cool, right? Okay.